In the last video, we were able to write down this triangle of binomial coefficients based on the recurrence relation we discovered. Next, I want to show you another interesting pattern. As long as x plus y is not 0, x plus y to the 0th power is equal to 1. X plus y to the first power is equal to x plus y. Notice that the coefficients of each of the variables is just 1. X plus y squared, you probably know, is x squared plus 2xy plus y squared. The coefficient on x squared is a 1, the coefficient on xy is a 2, and the coefficient on y squared is a 1. Next, let's try to figure out what x plus y cubed is, even though you can already probably figure it out. Rather than memorize a formula for this, we're going to actually use the distributive property. So this is x plus y times x plus y times x plus y. For each of the three factors, we are going to choose an x or a y. So the options are xxx, xxy, xyx, yxx, xyy, yxy, YYX, and YYY. Typically, at this point, we would regroup our terms. So we have 1 x cubed, which is the one way to choose 3 x's. We have 3 x squared y's, which is the number of ways to choose 2 x's out of 3 factors. We have 3 xy squareds, which is the number of ways to choose 2 y's. And 1 y cubed, which is the number of ways to choose 3 y's. Of course, these are the coefficients in the third row of the binomial triangle. And you can check for yourself that x plus y to the 4th power is x to the 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4th. All of this can be summed up by the binomial theorem, which says that x plus y to the nth power is the sum of all of the n choose r's times x to the n minus r times y to the r. Because binomial coefficients are symmetric, it really doesn't matter which one's x and which one's y, so long as their powers add up to n. As an example, let's calculate 1 minus x to the 5th power. Here, x is equal to 1 and y is equal to negative x. Since this binomial is being raised to the 5th power, I'm going to need 6 rows of the binomial triangle. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and the last number is 1. Therefore, this polynomial is 1 . The binomial theorem also serves as a pretty slick proof technique. For example, we can use it to prove that the sum of all the binomial coefficients along a fixed row n sum to 2 to the n. The proof is in noticing that the sum is the same as the sum from 0 to n of n choose r times 1 to the n minus r times 1 to the r. According to the binomial theorem, this is just 1 plus 1 to the nth power. In other words, we're using the binomial theorem where x and y are both equal to 1. Of course, 1 plus 1 is 2, and that completes the proof.